So before we start our discussion for this meeting, let us just have a summary of what we have studied from our previous discussion. So last meeting, we have learned that it suffices in the flexural design of reinforced concrete members to apply only the limit states of stress at failure for the choice of the section, provided that other requirements such as serviceability, shear capacity, and bond are met. But in the design of pre-stressed members, however, additional checks are needed at the load transfer and limit state at service load, as well as the limit state at failure, with the failure load indicating the reserve strength for overload conditions. All these checks are necessary to ensure that at service load, cracking is negligible and the long-term effects on deflection or camber are well controlled. So we have seen last meeting that uh, for the case of the flexural design of reinforced concrete members, we just usually check the limit state of stress at failure for our choice of the design section sufficient enough to withstand the given demand or loads that to be carried by the reinforced concrete. So it's like we are designing the member at ultimate load condition. So that's for the case of the reinforced concrete members. But for the case of pre-stressed concrete members, when we design pre-stressed concrete members, we don't just check the limit state at failure. We don't just check what particular section can withstand the ultimate loads that will be expected to be supported by the member that we are designing. But also, we also uh, do additional checks, which are the checks uh, of the stress at the load transfer and at limit state at service load. So we don't just check the pre-stressed concrete member that we are designing with respect to the limit state of failure, with meaning we don't just provide a section that is sufficient enough to withstand all the ultimate loads that are expected to be carried by the pre-stressed concrete member that we are designing, but we also uh, uh, conduct additional checking for the particular section that we are supposed to choose with respect to the load transfer and the limit state at service load. So why are we doing these additional checks? So to make sure that at service load condition, cracking will be negligible and the long-term effects on deflection or camber are well controlled. In fact, that's the main purpose of pre-stressing in the first place. We want to counter the effect of the tensile stresses that is or that are being induced in a pre-stressed concrete member at service load condition. That's why we are conducting pre-stressing. So we have to, in addition to the checking in the limit state at failure, we also try to check the particular criteria for checking at load transfer and limit state at service load for the design of pre-stressed concrete members, again, to ensure that there will be no cracking, to ensure that the tensile stresses that will be experienced by the concrete element at this stages of pre-stressing at load transfer and service load condition will not exceed the allowable stresses specified by the code. And then last meeting, we also learned how to design a particular Pristas concrete member with respect to service load design. So to design or choose the section, a determination of the required minimum section modulus SC and ST that can withstand all the loads after losses must be made first. So when we conduct service load design for a Pristas concrete member, we usually first check the the properties of a particular section that uh, that is compliant to the minimum section modulus SC and ST that came from the applied loads from the stresses from the applied loads that are supposed to be carried by the pre-stressed concrete member that we are designing. So we are finding at service load design, we are finding a particular section that has a section modulus greater than or equal to the section modulus required to withstand all the loads that are supposed to be carried by the member that we are designing even after the pre-stress losses already occurred. So that is what we are doing when we conduct service load design. Although service load design is dependent also on the profile of the tendon that we are supposed to put on the pre-stressed concrete member that we are designing. So if there will be a different eccentricity or profile for our tendon or for our pre-stressing reinforcement, there will be a different formula for finding the minimum section modulus. So last meeting we have learned two formulas, two different methods or two different cases for the computation of the minimum section modulus SC and ST. So the first one is for beams with variable tendon eccentricity. So for beams with variable tendon eccentricity, we have derived this minimum section modulus. So the section modulus of the section that we will choose as the section for the member that we are designing must have a section modulus greater than or equal to this section modulus that you will compute here using these formulas. And then we also derive a formula to find the maximum eccentricity so as to not exceed the maximum initial pre-stress that can experience by the pre-stressing reinforcement at service load condition. So we don't want that initial pre-stressing force to exceed that maximum initial pre-stressing force that we can compute on the design of the member at service load condition, because we don't want it to experience tensile stresses exceeding the maximum allowable tensile stresses specified by the code. So in order for us to ensure that the tensile stresses that will be experienced by the pre-stressed concrete member that we are designing will not exceed to the allowable stresses specified by the code, in order for us to assure that, we have to limit the eccentricity of our tendon profile or our pre-stressing reinforcement. So you can use this formula to find that maximum tendon eccentricity. And then additional formula is also or was also given just to find this stress acting on the centroid of the cross-section that we are designing. So you can use this formula if there is a limitation to the depth of the section that we are designing. So this H here is actually the total depth of the section. CC is the distance from the neutral axis to the extreme pre-compressed fiber. And the stresses that you are seeing here are all allowable stresses that you can find from the code. So that's for the beams with variable tendon eccentricity. So for beams with constant tendon eccentricity, meaning the eccentricity of the tendon doesn't change all throughout the length of the beam, the formulas that you can use for finding the minimum section modulus are this. So the section modulus of the section that we will choose must have a section modulus greater than or equal to this section modulus that you can compute using these formulas. And in addition to that, the maximum eccentricity that our tendon profile can have, in order for us to ensure that the stresses acting on the pre-stressing reinforcement as well as the concrete element will not exceed the allowable stresses specified by the code. So for this meeting, our intended learning outcome are first, to understand the underlying concepts on the deflection of a pre-stressed concrete element, and then to be able to calculate the deflection of a pre-stressed concrete element. So since we already know how to design the pre-stressed concrete element with respect to flexure, we must now understand how to compute the deflections that can be experienced by the pre-stressed concrete element that we are designing, as it supports its own weight as well as the remaining service loads, which are the superimposed dead loads and live loads. So without further ado, let us address our first goal, which is to understand the underlying concepts on the deflection of a precise concrete element. And then immediately after that, let us address our second goal, which is to be able to calculate the deflection of a precise concrete element. So we just have to apply what we have studied on this first goal that we have here. So without further ado, let us start the discussion.